Get started. So my name is Miro, and this is joint work with Alex Agakua, Carl Kosher, and Yoshi Kono from the University of Washington Computer Science and Engineering Department. And the motivation for our work was to try and understand the emerging technology, which is the modern automobile. And as you probably know, it's increasingly becoming computerized and connected. This is just a diagram of some of the embedded computing units that are under the hood if you were to look at the communication network that's occurring in a modern vehicle. And sort of a more formal diagram of that is represented here, where you see the various controllers that are interacting over what's known as the CAN bus, or the controller area network. And as we've seen from many previous studies, security is a really major threat in this space. And various folks have demonstrated the kinds of things that you can do in this space if you were to actually gain control of that communication area network. You're able to jump on and essentially exploit a buffer overflow from the radio to inject packets and pretend that you're the brake system, and there's no verification happening, and so you can start to create all kinds of havoc to someone who's trying to normally operate their vehicle. So there's lots of effort now being done by manufacturers and OEMs in investing in securing these resources, and I think that this is an area that's seeing a lot of active research, both from industry and from academia. On the other hand, relatively little is known about the privacy risks in this space, and the risks, on the other hand, are steadily increasing as the data sharing marketplace of the vehicle is growing and growing. We see insurance companies who are trying to help you save by figuring out whether or not you're a good driver. We see lots of these solutions which you can purchase from Amazon and plug into your car, and then tether to your phone and add all kinds of smarts to your automobile. There's also lots of interest from the government in trying to make cars safer through vehicle-to-vehicle communication and vehicle-to-infrastructure communication. So our goal was to try to understand exactly privacy from the perspective of driver identification. So we wanted to understand whether we can uniquely identify which amongst a set of N people is driving by using snippets of the most basic vehicle sensor messages that are happening in the car network. And we chose driver identification for numerous reasons. One, we felt that it was intellectually challenging. The chance of correctly guessing the driver given a set of N drivers is 1 over N, as opposed to some things like categorical distinctions like, is this driver drunk or drowsy? And also those kinds of distinctions are really difficult to get with IRB approval. We really wanted to see if we could avoid having to ask our university to see if we can give people alcohol before getting behind the wheel. So we also find this is an important problem by communicating with various car manufacturers and startups who are really interested in understanding the space of driver identification. There's lots of positive and negative uses that can occur with this data. On the positive side, you can imagine something like being able to do theft prevention, and on the negative side, you could potentially implicate people in whenever they're breaking the law. So from a privacy analytics perspective, this was something that was very interesting to us, and we wanted to understand if we could set some kind of a lower bound on our expectations of privacies by focusing on the most simple components, the basic vehicle sensors. And we have a limitation of an N of 15 folks, which was partly imposed by the fact that this had to be a 3-hour study with each individual, but we still think that this is a significant number for a first study. So getting into a little bit of the details, this is sort of our experimental setup. The vehicle that we used was a 2009 Chevy Impala, and we connected to the onboard diagnostics port of the vehicle, which is where you get your car emissions checked, and also where you would plug into if you were trying to monitor the health of your vehicle with some of these new sensors that are commercially available. And we tethered that to a laptop and monitored from the list of 15 sensors that you see on the right-hand side of the screen there. Just for information purposes, these sensors have various reporting rates, as you can see from the 3 sensors that I've sort of tried to break down here at the bottom. So the brake pedal position is reported at a much more rapid rate than the currently available torque to the car. And they also have different ranges over which they operate. So our experimental design was, again, as I mentioned, 15 drivers, 8 male, 7 female, using the Chevy Impala. And we asked these folks to perform, driving in a parking lot environment, which was isolated from all other drivers, as well as a 50-mile open road stretch. And we tried to have the conditions be maximally identical. So we had the same start time for the experiments, and we also made them listen to the same sort of pop rock radio station. So the parking lot setup was is part of our university campus, was gracious to allow us to use a closed off section of the parking lot to perform these various maneuvers. So we had the drivers familiarize themselves with the car and perform 3 laps. The first of which was practice, and the second 2 laps which we used for analytics. And I'll show you a quick video here of sort of what it looks like from our dash cam, where the driver is performing a 3-point turn, and then they'll go around and perform a reverse weave through these 5 cones, and then they'll perform other things like a parallel park. And this is just a snippet from one of the 3 laps that they were asked to perform. And this is actually 2x speed, so this is just for illustrative purposes. But you can get a somewhat of a sense of what the parking lot section looked like. All right, we're coming up to the parallel park. All right, we'll stop the video there. Okay, so okay, so for the open road data section, open road part of the driving, the selection criteria for us was that we wanted to have the start and end on our campus, and we wanted it to be long enough so that folks would get familiar with the vehicle and start to exhibit their natural driving tendencies. And so this incorporated driving across residential, city, highway, and back roads. And this is just from one driver's trip. This is the velocity plotted over time. And you can notice that, for example, the green sections are all highway driving, and they tend to have high velocity, whereas some of the downtown driving, which is highlighted here in pink, ends up having a lot of stop and go, and so you end up getting these velocity peaks and valleys. Here is sort of a little bit of a deeper dive within some of those sections. So again, the downtown is the first one here shown in pink, and if you just look at some of the sensor values that are occurring during that time, the red is the brake, the blue is the vehicle speed, and you can see sort of the alternating pattern of brakes and gas. Interestingly, some folks tend to sort of push down on the brake pedal more so while they're parked rather than others. And then this here, the bottom plot is a sort of technical back road driving where there's lots of loops and turns. And let me just very briefly show you a little bit of that. Again, this is at 4x speed, so this is going quite fast. But you can see, this is kind of like an interesting section of Mercer Island around Seattle, where folks had a chance to sort of show off some of their fancy turns and stuff. So we tried to incorporate a mix of various driving conditions just to enable some of these unique driver fingerprints to come out. But as our results ended up showing, you don't actually need to do anything fancy to have people's diverse driving strategies come out. So just a word on how we did some of this data analysis. For each of the various sensor streams, we did some smoothing, resampling to get everything down to the same data rate, so 60 hertz. And then we did tiled sliding windows so that 25% of the windows were overlapped to allow for really large variations to not occur at window edges. And for each of these windows, we computed a bunch of statistics, such as min, max, average, various quartiles, and some frequency components as well, such as the energies and the bins. And then we scaled all of these features from the training data. So we did 10-fold cross validation, and during each training fold, we would figure out what the scaling parameters were, so the average and the standard deviation, and then we would apply the same scaling to the whenever we did our test queries. One interesting thing about the way we did the classification here was that unlike sort of maybe traditional methods where you do one versus all comparisons, we did a matrix of pairwise sort of specialized classifiers. So what I'm trying to show with the slide here is that you would take all of the sliding window feature vectors computed for one subject, which were part of the training batch, and you would combine those with all of the sliding windows features from a second subject, and that would allow you to train one specialized classifier that's able to distinguish just between those two subjects, and that would essentially be one cell of this matrix. So in order to, or at least the approach that we took here, is that we need to populate the upper section of this matrix, since it doesn't really matter whether or not you train a classifier between subject 1 or 2 or between subject 2 and 1, they're essentially the same. So the upper triangular section of this matrix is all you need, and for our purposes that meant that for n subjects we needed to train n squared over 2 classifiers, and actually in order to do retrieval or search over this matrix given a set of queries, you only need n log n lookups using this algorithm that we used Q-weighted. So long story short, the results of what we found I think were pretty compelling, and that is to say that you don't need very much data in order to be able to do positive identification over the set of subjects we looked at. So we reached 91.33% accuracy when all of our sensors were available just on the parking lot data, so those 2 loops, which were about 8 minutes in total. You could also use just a single sensor, and this was pretty interesting. It turns out that probably the most differentiable thing in people's driving styles is how they decelerate or how they use the brake pedal. And so if you just take about the first 15 minutes of the drive, which kind of looked like this, where folks were going from our university campus down to the Space Needle in Seattle, if you take these 15 minutes of driving, where people are doing merges onto the highway, a few lane shifts, and then a bunch of turns, then with just the brake pedal during this 15 minutes, you are able to identify drivers at a really high rate. I think we reached like 88% approximately. And then if you took just the brake pedal over the course of the entire trip, you were able to get 100% accuracy across our drivers. So I think, and of course, if you take all sensors across the drive, you get 100% very easily. One last thing I'll mention is this extension that we did to try and understand how stable the fingerprint of the driver was across different days. So for that particular study, we had one driver repeat 5 days of this 22-mile trip from the university, and whenever we used those new trips as part of a query against our old data set where the driver had performed the same trip that everyone else did, we ended up getting 91% accuracy. And whenever we excluded the driver's data from the data set and then tried to query with their new instances of those 5 trips, we ended up getting lots of confusion. The network couldn't figure out who to attribute this data to, so it was guessing quite poorly. Which is to say that if we don't have a record of someone and you try to identify them, then that also isn't going to work well. Which again tends to say that the fingerprinting seems to be quite stable. This is some of the top sensors that were useful here: the brake pedal, as I mentioned, the steering wheel, and then the lateral acceleration. This is all available in the paper in case you're interested, and also just a hierarchical clustering of some of the correlations between the sensor data. I'll briefly just mention that I think we use an N of 15, and it would be very interesting for future work to try and understand how this would work for larger sets of candidate pools of drivers. One kind of encouraging result in this direction is that even if you take the most similar drivers and you sort of project their data into 2 dimensions, you end up seeing that there are some areas where they end up diverging, which is to say that with additional effort here, you could probably come up with some features that are really useful for fingerprinting. And again, this is future work most likely. So as far as defenses, we're just proposing some things here, and the thing that we think it could be promising is feature transformations of the data sort of in real time that would still enable some kind of inferences to occur. Or you could imagine these dongles that the insurance company plugs into your car. You could sort of get your own sort of defensive dongle that their dongle would plug into and run some kind of filtering techniques on it. Or you could alternatively inject packets by the car, maybe if you get manufacturer buy-in here, so that you would sort of obfuscate or at least introduce some noise that would make these kinds of privacy attacks a little harder. So that's it, and this is some of the summary and takeaway that I'll leave up during the QA.